All right. Well, hey everybody. Thanks for joining. My name is Brad Monday, and today I'm excited to talk to you about hyperparameter optimization with an open source tool called Tune. Now, hyperparameter optimization is a data science technique to basically get the most out of your training experiments with the models that you're building. We've had a lot of really great tech talks this year. For the remainder of the year, we'll plan to be here once a month, so stay tuned, and we'll make sure to update the calendar in our Discord channel so that you know exactly what's coming next. Okay, so today's tech talk is broken down into two components. The first will be conceptual, more classroom-based, where I want to walk through the concepts that you'll need to understand hyperparameter optimization. And the second component will be heavily in the demo portion. The first thing I'd like to do is define some objectives and kind of the purpose of who would benefit from this talk. Then we'll dive into some of those concepts I mentioned. What is machine learning and parameters? And then more specifically, what is hyperparameter optimization? What do we mean by that? And what are some examples of those parameters that we might tune? And then we'll transition into the demo, where I'll bring some of these concepts to real life and show from a practical standpoint how to implement them with some open source tools. Now, one theme to keep in mind throughout this talk is that what we're doing is searching for ways to optimize machine learning. There is a little bit of pun intended there, and you'll see why a little bit later. But ultimately, what we want to do, as I mentioned, is find a set of parameters that will optimize the performance of our machine learning models. So really, the things I want to do is make sure that I relay the information that you need to understand hyperparameter optimization, and then demonstrate how to actually take that to action. I think that beginner to intermediate level data scientists, machine learning engineers might already have experimented with and started building their own training pipelines. But being able to take that to a next step can sometimes be daunting. Hyperparameter search optimization is a technique that's well known, but this talk might help you overcome that bridge and start implementing it into your own processes. So, in order to understand hyperparameter optimization, I think we first need to understand the building blocks of machine learning models, and before that, really what machine learning is. So we'll start with this concept of a machine learning model that we've built. The idea that we can take lots of historical data, pass it through to this machine learning system, and teach it to perform some task. Right? Some of those tasks might include image classification or object detection. On the language front, speech transcription and text translation. Right? So that once we've trained our model, we can feed it data that it's never seen before, and out will come some predictions to inform some tasks, help streamline processes, and provide value. So that's kind of the high level understanding and overview of what AI and machine learning does. Now, let's take this a step further and talk about the construct or the building blocks of machine learning models. Well, they're built up of what's called parameters. Put generally speaking. And what we can do is break down parameters into two additional categories, two buckets. The first of which we'll call hyperparameters. These are parameters that can be set by the user or the model developer before executing a training experiment. These parameters are what control the behavior of the algorithm while it's being trained. Clearly different, and there's a clear distinction there from the model parameters. So model parameters are what you actually what learn during the training process and what make up a model, so that when your model is trained and you save a model file and you load in your pre-trained model, the contents of that model are those parameters itself. Some examples of this applied to some common machine learning frameworks would be coefficients of a regression model, weights and biases of a neural network, or cluster centroids of clustering algorithms. What we'll work with moving forward in the rest of this tech talk is that deep learning, the neural network use case, where but basically what we're doing is coming up with a way to decide the best combination of hyperparameters so that our model will perform the best. So that's kind of the building blocks of all machine learning models, and those parameters come in different ways, shapes, and forms, but ultimately are always persist and always exist. So let's take this to the next step. Let's say data scientists always have to construct and set up a training experiment. One way you could think of a data scientist in this setting is kind of like an architect. There's lots of decisions that you have to make. So again, as I mentioned, we'll be talking about neural networks here. Some of the hyperparameters that a data scientist may encounter and use as a part of the training experiment are train test split ratio, optimization algorithms, learning rate, activation functions, cost or loss functions, hidden layers, training epochs, number of clusters, kernel or filter size for convolutional neural networks, pooling size, batch size, and there are several others, right? But as you can see, the values of each of these parameters are things that data scientists have to decide, before executing that training experiment. So it's almost an experiment and model design process that has to happen before you even kick off that experiment. Not that we'll get too in-depth into each of these hyperparameters, but we'll reference some of them in some examples so you have an idea of what we're working with. You may have heard some of these. The first is train test split ratio. You've got your data set and you'd like to train a machine learning system to perform some task based on that historical data. Well, you're always going to want to split your data set into a train set, which will comprise most of that data set, and then a testing or validation set, so that throughout each iteration of the training cycle, you can freeze your model weights at that point in time and run the test or validation set through, again, that the model, those weights have never seen before, to validate the performance of your model at that point in time. Very commonly across the industry, you'll see an 80-20 split, where 80% will be your train set that will again be passed through in every training iteration, and then 20% that test or validation. Optimization algorithms are what we use to estimate the error between the current state of the model, in other words, predictions during a given training iteration, and the ground truth labels. And then this optimization algorithm will take that estimated information and update the weights of that network during something that's called backpropagation. Some examples of optimizations would be gradient descent, stochastic gradient descent, or the atom optimizer. Learning rate is actually a parameter to the optimization algorithm, and it represents the amount that your model weights will be updated at any point in time. So it will always be a value between 0 and 1. And the smaller or lower the learning rate, the more training epochs are required. Now, if your learning rate is too small, it can cause training to get stuck and take a very long time. On the flip side, the larger or the learning rate value would require fewer training epochs or iterations, but too large of a learning rate can cause your network to converge too quickly and have a pretty significant impact on performance. So this parameter alone, you can see, is really important when you're optimizing model performance and time, compute resources, etc. Activation functions are what transform outputs between layers. Some common examples would be sigmoid, softmax, leaky ReLU. Your loss function is a really important part, especially in your component in a neural network. It's what we use to actually measure the error between predictions or current state of a model during a training iteration and the ground truth labels. The relationship between optimization and loss functions is that optimization algorithms will estimate that error by taking the partial derivative of the loss function, in other words, the gradient. And so some examples of loss function for regression models would be mean square error, or for neural networks, cross entropy as one example. Hidden layers represent the number of layers between your input layer and your output layer. This will vary based on use case, architecture, task. Training epochs is just the number of iterations that you're going to pass your training data set forward and back through your network so that your model will continuously learn. Some examples might be 5, 20, 100. Number of clusters applies to non-supervised or clustering algorithms. Kernel and filter size apply to convolutional neural networks. It defines that window that we will use to iterate over an image. Typically, it's a perfect square, so 3 by 3, for example, 5 by 5, 10 by 10. And then batch size represents the number of inputs that you'll pass through during a given epoch or training iteration. Typically, you'll see powers of 2. So that's just a high level of some of the hyperparameters that we can work with when dealing with a hyperparameter search and optimization algorithm. Once we understand those, we can talk about what hyperparameter optimization actually is. So as I stated earlier, it's the process by which we'll select the best combination of those hyperparameters that deliver and yield and return the best performing model. So again, if I go back to this slide right here, we see all these different hyperparameters. Well, for each of these hyperparameters, there are several different values that you can select. And so what we're trying to do is find the combination of those different values to yield the best model performance. I like this visual to show an example where there might be 3 parameters we're working with: number of layers, number of neurons, and learning rate. And what we'll do with each combination that we see there is actually train a model for each of those hyperparameter combinations and see what the corresponding accuracy is that we get on the flip side. Some common terminology you'll hear that you can use these synonymously are optimization, tuning, and search. And some common implementations include RayTune, which we'll use today, HyperOpt, which is also an open source, really useful tool, and scikit-learn has some built-in hyperparameter search capabilities. So the way in which hyperparameter optimization actually works is through what's called a search algorithm. And there are lots of different search algorithms. I will talk about 4 or 5 right now. But something to keep in mind is that as you're choosing your search algorithm, there's a trade-off that you make. For folks just getting into hyperparameter optimization and hyperparameter search, there's a learning curve to understand how they work, understand what's best for which use cases, and so there's an ease of implementation with a trade-off of being sophistication. So the more sophisticated of an algorithm you get, the more optimal and more efficient your experiment is, and the quicker you can get to that optimal set of parameters. The first is manual search. So this is where, data scientists, you might be building a PyTorch training pipeline, and by brute force you can simply test all the different combinations as you'd like. But that obviously takes a lot of time and manpower. A grid search is what we're going to actually show a demo of today. Is highly parallelizable and will basically automate that manual search. So you can fix the number of the values you'd like for each of those hyperparameters that you'd like to search and tune. And the grid search will then run all of those experiments and output a model accordingly. Random search, instead of fixing a list of values for each of those hyperparameters, we'll simply randomly choose a value from a distribution of each of those parameters that they may be. It's less computationally expensive, will run less actual training examples and experiments, and avoids that brute force. But there's no guarantee that it will find the best solution. And the last 2 are derived from Bayesian optimization techniques called HyperOpt search and Bayes grid search. These are great for large-scale optimizations for models that have hundreds of parameters. You can scale it very easily across CPU cores, and it's very efficient, generally speaking. And the reason that is because it's an iterative approach that is more easy to understand in this visual representation I've created right here. So what we're looking at here is examples of the search space. So as I mentioned, I showed you a list of all those hyperparameters that you can tune, that you can try to optimize? Well, and each of those have several different options. So the more options you define, the larger your search space becomes to the nth dimension, very quickly. And again, that makes running experiments computationally very expensive. So if we look at the grid search, we see that we're just simply testing every combination in the search space. Whereas random will randomly choose, sets of hyperparameters in that search space. And then finally, the Bayesian search is a bit different, because what it will do is on each iteration, it will choose a set of hyperparameters that will improve upon the hyperparameters in the last iteration. So in other words, it looks at the results of the previous iteration and always tries to improve upon that. And finally, before we get into the demo, wanted to talk about kind of everything that we've now learned and how that applies to the example that we'll walk through. So starting from the beginning, we talked about the construct of a machine learning model. Consists of model parameters and hyperparameters. Hyperparameters are those that we can, as users and model developers, decide, right? And so what we're going to do today is conduct a hyperparameter search using RayTune and PyTorch to build an image classification model using the CFAR10 dataset. So the CFAR10 dataset is a very common dataset used for the image classification task. It's used for lots of baselines. And so by specifying a few different options for each of these hyperparameters, one of which will actually be the neural net architecture we use, that being ResNet, we will conduct this experiment and produce the best performing model based on these different combinations. We'll take this a step further, actually, and leverage another open source tool called MLflow Server. It's really useful for lots of different machine learning tasks and functions that you may need to execute. For this scenario, it integrates nicely with RayTune. What's great about it is, as you kick off your experiment, you can track the progress and final results of each combination very easily in a very friendly and easy to use user interface. So with that, let's dive right into the demo. All right. Okay, now the code that I've created is actually very closely aligned to two tutorials. So first, if you go to the RayTune site, you see all the great kind of scalable machine learning open source offerings they have. But if you click on examples, you'll see a lot of the common machine learning frameworks that it integrates with out of the box. Today we're going to walk through one of these PyTorch examples, and in fact, if I click on this link right here, it will take us to a training a classifier tutorial using CFAR10. Now, what I've done is taken this code and modified it a bit to, let's see, where's my code here? To show a few more things there. Okay, so I've built a single Python script called hyperparam.search.py. And the first thing I do, just like anybody who would be building a training pipeline, is import the packages I'll need. So PyTorch being the main one, right, with different modules specific to some tasks that we'll be performing. Torch Vision comes with those pre-trained model architectures, and so that's what we'll use to start off with. MLflow, so that we can track our experiments and pull up the easy to use UI, and then most importantly, RayTune. So this is the library that allows us to build and execute this hyperparameter search. What I'm actually going to do is work backwards and start with the RayTune part specifically. Okay. So the idea behind the script is we'll start by generating or instantiating connection to our MLflow client. We'll use that client to create a new experiment right here. We can use this to track the results of our RayTune run. And then what we've done is provided two options here. We can specify a basic search, which will just execute a grid search. That's one of those hyperparameter search algorithms I talked about. We will show that one today. But RayTune is convenient and does provide support for lots of other hyperparameter search algorithms. including the ones that I showed, and then even more than that. So the first thing we need to do is define this configuration dictionary. This is really where we have the opportunity to fix the values we'd like to run in these various combinations of hyperparameters. So we'll pass through our MLflow experiment ID, the directory where we're going to save our weights file. And then it gets into some of those hyperparameters that we talked about. So learning rate, remember I talked about that. It's a parameter that goes into the optimization function. What we'll do is randomly choose from this log distribution, or log uniform distribution, this optimization function. We're going to test two out: stochastic gradient descent and the atom optimizer. Architecture represents the different ResNet model that we'll start from. Of the various ResNet variants that we'll use that are available, we will use ResNet 34, ResNet 50, and ResNet 101. We'll add two options for pre-trained Booleans. What that will do is either, if set to true, download a pre-trained ResNet model, trained on the ImageNet dataset, or start from scratch. And then finally, the batch size that we'll use as we're training and passing our data through in each iteration. And then RayTune will do the rest. So all you have to do is kick off this tune.run script, pass through a train function I'll talk about in a second, your configuration, the resources that you'd like to use for this trial. So in this case, we'll run on 4 CPUs and 1 GPU, but you can parallelize this even further if you had more resources at your disposal. Number of samples just represents the number of times that we'll sample from the search space. In this case, we're just going to run one iteration of each of these 12 experiments. So I get that 12 number because there's 2 optimizers we'd like to test, 3 architectures, and 2 pre-trained options. And so 2 times 3 times 2 will be 12 different experiments. And then finally, we'll be able to add this callbacks parameter to track our experiment. So we'll kick this off. And what essentially that does is execute this train CFAR method. So if I scroll back up, we'll walk through what that does. We've defined this load data function, by the way, as a convenience wrapper around some PyTorch code that will download the CFAR10 dataset for us. The first thing we do here is define our model. And so as you can see, we've passed through that configuration dictionary to this train function. And we see that we're loading our model from the architecture that we specify in that configuration. Once we've got our network, we do have to modify the final layer a little bit because as you preload one of these ResNet models, it's trained to return an output of 1,000 inputs. Those 1,000 inputs correspond to that ImageNet dataset where there's 1,000 classes. Since the CFAR10 dataset only has 10 classes, we'll simply rework that fully connected layer and add only 10 classes here. We can define the device that we're working with. Since we have access to GPU, we can define that as CUDA. We'll cast our model to that device and then get into some more of these hyperparameters that I talked about. First thing we'll do is define our loss function, also known as a cost function or a criterion, as cross entropy. That's not a parameter that in this example that we will tune. Then we can set our optimizer. So again, we've got 2 options where we'll either set it to stochastic gradient descent, passing through the learning rate specified in our configuration, or the atom optimizer with that same parameter. And then the rest of this, we'll take our data, we'll use Torch's data loader functionality to do that train test split, load up a train set, validation set, and then construct our training loop. And so again, this is a very standard way to do this. In this case, we're only going to go through it 5 times. And in doing so, pass each batch of data through our model, compute our loss, and then kind of go through the exact same or the normal steps you would to execute the forward pass and then back propagation, update the weights, keep track of the training loss that we're recording, the training accuracy that we'll use to report. Same thing, we'll then go through a validation each epoch, report all those metrics. And then after a training run is finished, so after we've gone through all the training iterations or epochs we've defined, we'll then generate a test set that the model has never seen before, and calculate accuracy there. Now you could add on to this and track precision, recall, F1 score, any sort of other metrics you'd like, and very easily report those. Every time we see tune.report here, we'll notice that in MLflow, in a second when I pivot over there, that those metrics will show up accordingly. And then finally, what we want to do is save a weights file for every training experiment that we've run. Okay, so that train CFAR function is executed by RayTune. I went ahead and pre-ran this, and what you see in the terminal is basically a screen that looks like this, where we're printing out each of the 12 experiments, and you can track this in real time. So the number of iterations represents the number of epochs, total time, all the parameters that we've specified, etc. But I will show you the interface because it's a lot more friendly. So because we set up that MLflow client and defined an MLflow experiment, we can visualize our outputs right here. So we see I've run 4 different experiments in the last 24 hours or so. We can see our first experiment where we just ran a single set of parameters. Second, we simply modified the pre-trained parameter. So there's 2 experiments total run. And then the big one that I just showed you, we can see all the results for each of the 12 combinations of hyperparameters. So as we see this, we can track and compare the metrics captured during each run. We can compare the parameters. We see the different ResNet architectures, batch size, learning rate, optimizer, pre-train. And as we can see, there's 12 different combinations, right? What's very nice about this is that during training, you can click on any one of these experiments. You can see the parameters and where the corresponding model that was trained is saved, and then track some of the metrics in real time. So training loss, we'd expect the curve to go down. If we had more epochs, this would be smoother and look a little bit nicer, but we cut this particular experiment short. And then what we're left with is this list of models. And so if I were to go back to my VS Code editor, we saved each of the 12 model runs in this model weights directory. And if I wanted to then take this and start to deploy it into production, I would have a very easy way of doing so. But throughout the entirety of this tech talk, we covered the experimentation side of machine learning in a way to easily use open source tools to conduct your own hyperparameter search and automate and streamline your training process to ultimately yield and create experiments that build the best performing model. I will stop sharing my screen. Oop. I know how to do that. And close it out there. Thanks everybody for joining. Hopefully you learned something, and we will be over in general if you have any questions. Thanks.